Thank you for the introduction. It's a pleasure to be here. So I would like to speak about a few molecular sources that may be interesting when considering future Attosecond experiments. I've made my goal to give a sampling of molecular sources that could, and in some cases already are, being used in Attosecond experiments. But for the most part, I will not guide you with thoughts on how they are or could be used. That hopefully leaves some room for your imagination and leads to new experiments. Let's see how it goes. So, with the intention to introduce a few possibilities of molecular sources that could be useful for Attosecond experiments, I want to outline their working principles and give an idea of their strengths, as well as where their weaknesses may be. The outline is organized here. So we will look at free jet expansions, Laval expansions, some aerosol particle methods, and liquid microjets that can be used to produce molecular targets of increasing size in general. It should be noted that this is a small sample of the available molecular sources, but it can serve as a good starting point when considering sources for your future Attosecond experiments. Any one of these techniques warrants more than a lecture of its own, but I will try to give you a taste of each and show a couple of real-life experimental setups along the way. The molecular sources we will be looking at today will be operated under various conditions and in very different flow regimes. I will not go into detail about all the differences, but will try to give some context for each method and use a few simple quantities to describe the flow regimes. The Mach number is the first such quantity. It is a dimensionless ratio of the velocity of a gas or a medium over the local speed of sound, where the speed of sound is defined here. The ratio of heat capacities, or gamma, equals 1 + 2 over the accessible degrees of freedom, as I show here. In our first two molecular sources, the free jet and the de Laval expansions, the Mach number will be greater than 1, meaning the resulting molecular beams will be supersonic. In that way, they are similar. However, they will exist in very different flow regimes, which can be characterized by the dimensionless quantity, the Knudsen number. It is the ratio of a molecule's mean free path to the characteristic length of a given experiment. In our case, we could say the length of the molecular beam's propagation. The free jet produces a beam with well-defined velocity that propagates in vacuum and consequently has mean free paths on the meter to kilometer scale. The Laval expansion generates a beam with well-defined temperature and pressure conditions and operates in or near the continuum regime, so has many collisions during its propagation. Depending on what you want to study, the choice of which source you may want to use becomes straightforward. Let's have a look at both. So we start with free jet expansions. Free jet expansions can be used to produce beams of gas phase molecules or molecular clusters. I'll restrict myself to neutral species for the following. Molecular clusters are interesting targets for future Attosecond experiments as they form the connection between the gas and bulk phases and often exhibit properties between the two. Small molecular clusters are at the limit of what can be accurately described by high-level theoretical models and are very much suited for detailed investigations. Several experimental techniques can be used to study molecular complexes. In all cases, efficient production methods are required. Since molecular clusters are often held together by weak van der Waals interactions, many of these complexes are not bound at room temperature. So an efficient production method would involve lowering the temperature. Yeah. One way to produce very low temperature gas phase molecules and molecular clusters is to use molecular beams formed in a free jet expansion. Good. Here's an example of a free jet expansion. You've probably seen this before. From a short conversion nozzle. If the stagnation pressure is higher than the pressure outside the nozzle, the gas is accelerated towards the exit. Provided that the ratio P0 over PA is sufficiently high, sonic speed, a Mach number of 1, is achieved at the nozzle exit. The pressure at the nozzle exit becomes independent of the chamber background pressure, and the flow is said to be underexpanded. As a consequence, further expansion occurs, starting from the rim of the nozzle with so-called Prandtl-Meyer expansion waves, indicated here with these dashed lines. The flow becomes supersonic, with the Mach number becoming much greater than 1, and the Mach number increases with increasing distance from the nozzle. Since the supersonic flow is unable to sense the boundary conditions downstream, it overexpands to pressures lower than PA. The expansion is recompressed by a series of shock waves at the jet boundary, called barrel shock here. And consequently, the cross-sectional area of the expansion decreases and the pressure increases. At the so-called Mach disk, compression waves reflected from the jet boundary intersect, and the initial pressure, PA, is reestablished by a shock wave normal to the expansion propagation. Good. Oh, hang on one second. The Mach dislocation is given simply by the diameter of the nozzle, the stagnation pressure, and the chamber pressure. Okay, there, my computer's back. Phew. My computer is freezing. Oh no. Okay, hang on one second. Okay, there I'm back. Okay, sorry about that. Okay, good. So where was I? So a free jet expansion is terminated at the location of its Mach disk, like we saw here, which is dependent only on the ratio of the stagnation pressure and the chamber pressure, as well as the nozzle diameter. And so it's not dependent on any intrinsic properties of the gas that we're expanding, conveniently. In order to make a molecular or cluster beam, we need to place a skimmer inside the zone of silence or before the Mach disk, as we've shown here. The skimmer works to cut out a cold slice of the free jet expansion and forms a beam that can be passed on to other chambers, traveling at speeds of typically a few hundred to a few thousand meters per second. The resulting beam will be quasi-collisionless and with a well-defined velocity and divergence dictated ideally by the diameter of the skimmer and the distance from the nozzle. Rotational temperatures in the molecular beam can drop to typically a few Kelvin, with vibrational temperatures being typically warmer, 10s to 100 Kelvin, depending on the expansion conditions. Here I show a table of the location of the Mach disks for various stagnation and chamber pressures using a 100 micron nozzle. We see that expanding 10 bar stagnation pressure into a chamber of 10 to the minus 2 millibar would produce Mach disks that are only 7 centimeters downstream from the nozzle. Decreasing the chamber pressure pushes the Mach disk further downstream, so much so that at lower chamber pressures, it can be approximated that the destruction of the free jet is dictated by the chamber walls and skimmer rather than the pressure differential. So then chamber design becomes important. Okay. Free jet expansions are not novel in themselves, but they are evolving with increasingly intense expansions. The increased intensity brings the need for more thought to go into generating and skimming the expansions. On the left, we see a simulation of 10 to the 22 atoms per cubic centimeter impinging on a popular 1 millimeter diameter skimmer shape that was used extensively with low intensity continuous beams. The simulation represents the flow of a collimated cold stream of neon atoms and is a good example of a clogged skimmer. The base has less than 2%. The base of the skimmer has less than 2% of the incoming beam intensity. In this case, the skimmer shape is wrong and the entering beam intensity is too high. So severe loss of the beam intensity is caused by the shockwave structure near the skimmer entrance, you see here. To achieve the best transmission results for intense molecular beams, like for example from an Evans-Levy valve, it's often necessary to employ a large diameter skimmer, say 2 to 4 millimeters, and move the skimmer 10 to 20 centimeters downstream from the nozzle. These requirements need to be taken into account when you set up your experiments and design source chambers. Furthermore, there's the question of how sharp the edges of a skimmer need to be. Here's a graph of temperature rise as a function of axial distance from the skimmer, where the skimmer is placed at x equals 0. Again, the flowing gas is neon with a number density of 10 to the 22 atoms per cubic meter. The skimmer entrance aperture is again 1 millimeter and placed at x equals 0. This temperature increase that we see for various skimmer rim thicknesses is only momentarily increased, but the extreme temperature increase can cause the fragile clusters that you want to generate to be destroyed. So damaged or blunt skimmers should not be used. In some cases, even cooling the skimmer is helpful. On the right, we see an internal and external shock waves generated on a skimmer from an intense plume of a pulsed valve. You see shock waves here where your skimmer is there. Okay. Yeah. It was shown that cryogenically cooling the skimmer reduced the shock waves and increased the amount of gas transmitted by over a factor of 5 in some cases. In these two graphs, we see normalized transmitted intensity as a function of stagnation pressure in the valve and distance from the nozzle to skimmer on the right side. We see that for the room temperature skimmer, we have a plateauing of the intensity where we would expect an increase with increasing pressure, which is borne out in the cold skimmer. Also, when pushing the nozzle closer to the skimmer, one would expect an increase in intensity, which is found when the skimmer is cooled. All this to say, please pay attention to how you set up your free jet expansions. It seems simple, but with intense expansions, there are some pitfalls that could cost you a lot of molecular beam intensity and signal in your experiment in the end. Okay, good. So there are many ways to make molecular clusters, Which one is best for you depends on the substance you want to use. If you want to study something that is a gas in your lab, you can mix and co-expand it with some carrier gas. The seed to carrier gas ratio, as well as the stagnation temperature and pressure, give you the ability to tune the properties of your beam, from velocity to the extent of clustering. If you're wanting to expand a liquid, you can bubble carrier gas through the liquid using the temperature dependence of its vapor pressure, and vary the ratio of your seed and condensable gas, and then co-expand it. You could also consider generating a molecular beam with a pulsed expansion and passing it through a pickup cell. Pickup cell. This is as shown here. This is far from an exhaustive list, but here's to give you some ideas for possible experiments in your work. Okay, let's say we have produced a molecular beam containing weakly bound clusters that we would like to use for some Attosecond experiment. The distribution of clusters present in the beam depends sensitively on several factors. In an ideal world, we would have a sensitive, independent, in situ, non-destructive method to determine the cluster size distribution that will be used in whatever experiments that you're going to dream of. Here are a few ways that are used to determine cluster size distributions of weakly bound, neutral molecular aggregates. Scaling laws use parameterization of an idealized expansion to predict clustering in a real expansion. This is not an in situ method, and in some cases can be quite far from reality. That said, depending on your experiment, it may be all you have, or precise knowledge of your cluster distribution may not be critical. Soft ionization and mass spectrometry detection is an in situ method that can yield detailed information on clusters in your experiment, but also has its limits. For example, ionization-induced fragmentation is significant in some cases. Light scattering methods, here, are also in situ measurements of clusters. So typically you'll need particles of, let's say, 10 nanometers or more, and that's many thousands of monomer units in most cases. So it's not really useful for small aggregates. Here I want to highlight the need for reliable independent methods for cluster size determination, especially when working with weakly bound molecular clusters. And this is more of an issue when dealing with neutral clusters. With charges, it becomes easier. Good. Let's consider a mass spectrometry solution to determining cluster size distributions of neutral molecular aggregates. Clusters of different substances are formed in vacuum by pulsed free jet expansion, as we just saw before. After passing a temperature-controlled oven filled with sodium metals, the clusters pick up a sodium atom and then enter an ionization time of flight chamber where they're ionized with UV light that ionizes the sodium atom but not the cluster itself. Or these clusters pass through a cold oven, do not pick up the sodium, and are directly ionized by VUV light. We'll call this experiment 2. So we looked at four different cluster types. The aim of this study was to see how intra-cluster reactions after single photon VUV ionization of weakly bound clusters affect cluster fragmentation. Two classes of clusters were looked at. Those with minor ionic reactivity, so methanol and water, and those having extensive ionic reactivity, acetic acid and dimethyl ether. Good. Here we see a series of mass spectra for each substance. The top panels show the sodium doping method, or the experiment 1, and the lower panels show the results of direct ionization, experiment 2, using 13.3 eV photon energy. The spectra show ion intensity as a function of n, the number of molecules per cluster. The upper x-axis gives the corresponding diameter of these clusters. Upon VUV ionization, a fast proton transfer occurs in all four systems as a first step, releasing up to about 1 eV of energy. In ionic water and methanol, no further reactions occur. And we see that the UV and the VUV spectrum agree quite nicely. So both methods would be considered soft ionization methods that give us a good picture of the size distribution of our clusters. However, proton transfer provides initiators for radical chain reactions in ionic dimethyl ether and acetic acid clusters, here and here. The intercluster, we see here that the UV mass spectrum has significantly larger clusters than the VUV mass spectrum in both cases. So these intercluster chain reactions lead to a decay of the neutral dimethyl ether and acetic acid molecules into small stable products. The volatile products escape from the clusters so that fragmentation is not visible in the individual mass spectra. This shows that VUV ionization can cause significant cluster fragmentation. Because of this, direct VUV ionization cannot always be considered a soft ionization method for these weakly bound systems. This statement is not limited to VUV ionization, but also holds for other direct ionization methods, such as electron impact. I highlight this work to show independent, reliable cluster and aerosol sizing methods are crucial for any further size-dependent studies that you may want to conduct. Okay, let's go on to Laval nozzles. Uniform expansions can overcome some limitations of free jets by maintaining local equilibrium at all points in the flow. While not without their own limitations, these flows can provide an alternative, sometimes more suitable environment for a variety of applications. A key to producing a uniform expansion is the Laval nozzle. De Laval, or converging diverging nozzles, produce expansions under equilibrium conditions. Here we see a thin slice through the center of a cylindrically symmetric nozzle. On the left is the stagnation region with relatively high pressure and known temperature and pressure, density, velocity of 0 and Mach number of 0. The gas accelerates towards lower pressure to the right, with clustering formation under well-controlled conditions possible as it cools and expands. Laval nozzles are particularly well suited for situations where well-defined temperature and pressure conditions are needed. Their disadvantages include the need for stronger pumps and involved design and fabrication processes. Before we continue, another picture I would like to bring for you to consider when discussing Laval expansions and later for aerosol methods in liquid jets is the idea of laminar versus turbulent flow. Laminar flow is where the viscous forces are dominant and is characterized by smooth, fluid motion. Turbulent flow is dominated by inertial forces which tend to produce chaotic eddies, vortices, and other flow instabilities. These flows can be succinctly characterized by the Reynolds number, which is a dimensionless quantity used to help predict similar flow patterns in different situations. The Reynolds number is defined as the ratio of inertial forces to viscous forces. Yeah, matching the Reynolds number is not sufficient to guarantee that two flows are similar, though. Fluid flow is generally chaotic, and very small changes to shape and surface roughness can result in very different flows. Nevertheless, the Reynolds number is an important guide and is widely used. In the cases that we look at today, we will be working with laminar flows for the most part, so low Reynolds numbers. Just to give you a picture of how this will look. Okay. In order to describe the flow of a Laval nozzle, let's consider a one-dimensional flow of an ideal or inviscid and compressible gas with isentropic flow. I could answer that question now. If you cool the skimmer, how do you avoid ice plugs at the opening? I believe it does have some lifetime because you do collect gas onto the skimmer itself. So this is not something that you can work with for days. Depending on your gas load, it can, I don't know how long it will take before it plugs. The gas itself will sweep out a hole. I've seen this for myself for different expansions. So the question, we can come back to it. Okay. Cool. All right. So we go back to the Laval nozzle. The Laval nozzle is connected to a so-called stagnation volume that we see here, with stagnation temperature and stagnation pressure. The pressure gradient between the input and output of the nozzle is the driving force of the expansion. The bottom panel here shows the behavior of the pressure P and the temperature T and the velocity U inside the Laval nozzle and in the post-nozzle flow. The velocity reaches a constant value UF near the nozzle exit. The pressure and temperature decrease drastically in the Laval nozzle and then reach a constant value. The gas in the nozzle can become supersaturated and cluster growth induced. Experimentally, the background pressure here is matched with the static pressure in the post-nozzle flow, PF. The background gas acts as an extension tube. As a result, the uniform conditions generated in the nozzle are extended into the post-nozzle flow. By recording the stagnation conditions and the impact pressure, which is a dynamic pressure in the post-nozzle flow, one can determine the Mach number by using the Rayleigh-Peto equation with some approximations. And with this Mach number, the flow temperature, flow pressure, its gas density, and flow velocity can all be calculated. Oh. In order to design and predict nozzle characteristics, the expansion is simulated with computational fluid dynamics software. In this case, Fluent ANSYS. Here we see the results of a simulation for a Mach 4.4 nozzle. The top panel shows a contour plot of flow temperature with this color bar inside the nozzle, shown here in gray, and in the post-nozzle flow. The y-axis gives a radial direction, with 0 being the center line of the nozzle. The x-axis is the axial distance, with 0 at the nozzle exit. Yeah? A uniform post-nozzle flow is maintained over several centimeters, as shown here, or here. The simulated impact pressure profiles at various axial distances gives you a feeling of the usable dimension of this cylindrically symmetric beam. So here are impact pressure traces for a given radial distance. I've made the radial distance axis parallel to the radial distance axis on this side. So you see the width of this post-nozzle flow It has a radius of about 5 millimeters, where we could sample under uniform conditions. Yeah. So some deviation between design, simulation, and experiment are typical for Laval expansions, even with great care taken in doing all of these steps. I also note here that the gas density in the post-nozzle flow is as high or higher than many free jet expansion molecular beams. Laval expansions can be used to produce equilibrium temperatures down below 10 Kelvin and up to above 200 Kelvin. Yeah, good. So here's a example experimental setup. Here we see a Laval expansion source here, expanding it, and we expand a mixture of propane and argon. The uniform flow of the Laval nozzle exit is extended into this post-nozzle flow region, shown here as the dashed lines. Yeah. Typically, the chamber pressure needs to be in the range of 0.1 and 1 millibar. So it's pumped by a Roots blower and a rotary piston pump. The pumping is involved and critical in this chamber. The impact pressure, PI, is measured by this transducer. By translating the transducer in the radial direction and translating the Laval nozzle in the axial direction, we can map out the conditions over the whole post-nozzle flow, yeah, and determine all of our properties, as I showed in the previous slide. Okay. The cluster size distribution present in the post-nozzle flow at a specific saturation can be detected by soft ionization mass spectrometry, as we saw for the free jet. For that purpose, the central part of the post-nozzle flow, here, the central part of the post-nozzle flow, shown here at the skimmer, is skimmed out and passed through a differential pumping chamber and into a ionization time of flight spectrometer chamber. The degree of clustering for a given set of conditions can be changed by translating the nozzle in the axial direction, essentially changing the time spent in the post-nozzle flow before being probed. Here, we see a mass spectrum of propane clusters generated in a Laval expansion. The ion intensity is plotted as a function of n, where n is again the number of molecules per cluster. In this example, clusters of up to n equals 8,000 or up to more than 8 nanometers in diameter were produced. So we can generate large clusters. If there's no question about Laval nozzles, we can go on to aerosol particles. Good. So let's move on to aerosol particles and produce beams of particles between a few nanometers to microns in size. So overlapping and extending the size range from what we just saw with the supersonic expansion methods. Aerosol particles and droplets are ubiquitous in the atmosphere of Earth and other planets, as well as in interstellar space. They are involved in diverse chemical and physical processes. Aerosols are relevant for many technical processes, and what I like to do can be exploited for fundamental studies. Questions about aerosols that have intrigued scientists for decades involve understanding why and how some of their properties differ from those of bulk materials. That is, how surface, size, shape, and confinement alter analogous bulk properties. Okay, let's look at an example of confinement effects in dielectric or molecular aerosol particles. Here we see two limiting cases. Nanofocusing, we'll call it, and shadowing, respectively. Nanofocusing is a resonance phenomenon that occurs for particles that absorb only weakly at the wavelength of the incident radiation, propagating here from left to right. In other words, the imaginary part, K, of the refractive index is small at that wavelength. In the case shown here, most of the intensity is localized at an intense hotspot close to the particle's surface on the far side from the incident light. Shadowing dominates when the particle absorbs the incident radiation strongly. That is, when K is large for the incident wavelength. In this case, the local intensity is highest on the incoming side. Yeah? And this is basically all of the light is attenuated by this point. Yeah. The right-hand figure, in the right-hand figure, we can also change light intensity patterns inside of dielectric particles by simply changing their size. Here, we see calculated light intensity patterns generated by interacting 10 eV or 124 nanometer light with different size particles, 5 nanometer radius, 100 nanometer, and 500 nanometer radius. The corresponding circles show cuts through each of the spherical particles. No? We see that when the particle is much smaller than the wavelength of the light, there's uniform intensity over the whole particle, near uniform intensity. As the particle radius becomes comparable to the wavelength of the light, we see a variation in the light intensity inside the particle. The variation becomes more extreme as the particle radius increases, something to take into account when playing with aerosol particles. Here we have an example of a change from shadowing to nanofocusing for DOP droplets of 200 nanometer radius, as the incident wavelength is changed from 203 nanometers to 209 nanometers. The N and K of DOP's refractive index over this wavelength range are shown here. In the left-hand column, we have the calculated light intensity squared, because it's a 2-photon ionization, inside the droplet. We see for the 203 nanometer incident light, most of the light is absorbed on the incoming side, correspondingly relatively high K value. As we change the wavelength away from the absorption peak, the K value decreases, and the light intensity shifts towards nanofocusing in this case. Yeah. On the right-hand column, we have experimental photoelectron velocity map images that correspond to these different wavelengths. We see that the change of just a few nanometers in incident light can produce a shift in the experimental image from preferentially forward photo emission to preferential backwards photo emission. These types of effects need to be considered when constructing, for example, pump probe experiments, as it is possible to localize light intensity in a particle by careful selection of material, size, and photon energies. In the XUV and soft X-ray regions, materials tend to be strongly absorbing, so would be in the shadowing regime. There are several ways to produce aerosol particles, and we come into contact with many of them in our daily lives. They often involve spraying, atomizers, nebulizers, electrospray, to name a few. With the exception of the gas dynamic virtual nozzle at the very end of the talk, all the aerosol examples that I show today involve atomizers, which are, simply put, continuously flowing perfume bottles, schematically shown here. We will use them to form stable, continuous streams of polydisperse, or polydisperse is having many sizes, aerosol particles with the nanometer to micron size range. Many substances are possible to produce like this. I list a few here. And here, to give you a feeling of how many molecules of water are in a droplet of different sizes, I've listed it here. I find it interesting. Good. As as I showed, the properties and observables of aerosol particles can depend sensitively on their size. It's critical to know the sizes that are present in your experiment. And for detailed experiments, it really helps to work with size-selected or monodispersed aerosol particles. With this in mind, let's consider a differential mobility analyzer, which can be used to measure the size distribution of aerosol particles or to select a size from a distribution. A DMA classifies particles according to their aerodynamic electric mobility. Since a DMA can only classify charged particles, the particles are brought into a known charge distribution by a radioactive or X-ray neutralizer. It basically makes a known charge distribution, so all of the corrections can be made to determine the aerodynamic diameters in the end. Okay, they work like this. A laminar flow of neutralized or charged, sounds funny, polydispersed aerosol enters a cylinder with a rod in the center. Yeah? An electric, a voltage is applied on this rod, and an electric field is generated between the cylinder wall and the rod. The aerosol enters here, flows this way, and according to its electrical mobility is pulled towards the rod, and selected electric mobility diameters come out at the end. And you have monodispersed aerosol. Good. So we can determine the size and select the size of aerosol particles using a DMA, or Differential Mobility Analyzer. Good. The size distribution of an aerosol can be measured using a so-called scanning mobility particle sizer here, which is a DMA, as we just saw, and a particle counter, which is a separate device that, for us, we'll just call it a black box. It measures the number of particles. Okay. The classifying voltage of the DMA is ramped in a stepwise manner while the transmitted particle concentrations are monitored continuously using a condensation particle counter here. Let's consider a real-life example using the low vapor pressure DOP that I mentioned before. We generate a continuous flow of polydispersed aerosol particles with our atomizer, then pass the flow through a neutralizer to produce our known charge distribution. After that, the particles enter the DMA where they are sorted by their mobility in an electric field. By scanning this voltage in the DMA and monitoring the transmitted particles, as we can produce plots of particle number density as a function of size. Here, in this case, we see that we have significant abundance of particles between 100 and 700 nanometers. Okay. Now we know we have many sizes and we know their concentrations. This is great. Let's say we would like to work with 200 nanometer particles. We can fix a DMA voltage, this DMA voltage, to produce a voltage to only allow 200 nanometer particles to transmit. Good. To check if that works, we can pass the output to an SMPS, just like we did here, and measure, again, particle concentration as a function of size, and split the flow to go to your experiment. Yeah? Wrong way. So if we measure the output of this DMA, we see now that we have only particles with an electric mobility diameter of 200 nanometers. So that sounds good. Let's hurry up and take data before something breaks, because something always breaks. But we should remember that the electric mobility was dependent on size and number of charges. Not all the particles in this peak are singly charged particles of 200 nanometer size. there are multiply charged particles with larger sizes. This may or may not be a problem and can be mitigated, but knowing that it's the case is already an important first step. Good. Another way to classify particles that does not base its working principle on charged particles is an Aerodynamic Aerosol Classifier, or an AAC. The AAC consists of two concentric cylinders rotating at the same direction with the same rotational speed. The aerosol enters a gap here between the two cylinders through a slit of the inner cylinder, and a flow of particle-free air enters between the two cylinders. When the cylinders are rotated, the particle experiences a centrifugal and drag force in the radial direction. No? Okay. The radial forces cause the particles to move towards the outer cylinder, and particles with a narrow range of particle relaxation times exit with the sample flow here. Particles with longer relaxation times impact the outer cylinder, and particles with a smaller relaxation time exit with the exhaust flow. Here, this particle relaxation time is equal to the particle mobility and its mass. It does not need to be charged, so we can work with really neutral aerosols. Good. By changing the rotation speed of the cylinders in the AAC, we can change which particle diameter is transmitted. To give you a feeling for that, I list two extremes for the AAC. Good. Good. So the generation and classifying methods that we've been talking about take place in the laboratory or at pressures of around 1 bar. The aerosol can be transferred to vacuum where attosecond light pulses and electrons propagate. One way to bridge the pressure gap between the lab and your high vacuum, if you want to use it, probably do, is to form a beam of the particles with an aerodynamic lens stack, shown here, for example. An aerodynamic lens stack consists of a series of orifices of decreasing size through which dilute aerosol is channeled. The gas containing the aerosol of interest forms streamlines that restrict and expand at the orifices. You know? This produces a lensing effect for the aerosol particles and forms a beam of particles as it delivers them to vacuum. The gas is not focused, but does need to be pumped away and can be a considerable gas load. Yeah. So I mentioned already a couple of times the need for nanoparticle characterization that would be ideally done in situ, non-destructively, yada. Several groups have been developing such techniques over the last years. A recent paper by Cooper and co-workers used a light sheet imaging as a simple non-destructive in situ method to record transverse particle beam profiles, including absolute number densities as well as velocity of particles passing the light sheet. It's a relatively simple experimental setup shown here, consisting of the optical setup to generate a cylindrical sheet, a cylindrically focused light sheet with a continuous wave laser, an aerodynamic lens stack to form your nanoparticle beam, and a microscope detector setup for recording the scattered light. The measurement is based on light scattering of single particles as they traverse this light sheet. The histogram reveals the absolute particle flux, and we see this as a function of distance from the aerodynamic lens here, 4 millimeters to 8 millimeters. Yeah. Note that the aerosol beam is focused with its tightest waist here at 7 millimeters from the exit of the aerodynamic lens stack. Its full width half max is 45 microns. And in this case, the quantitative flux was only 4.3 particles per square micron per second. That's That's artificially low. They can go many orders of magnitude higher than that. Using polystyrene beads with known size and Mie scattering simulations, the velocity of the particles passing through the light sheet could be determined. And I show the velocities as a function of distance from the injector here. The particles were traveling between, say, 130 and 160 meters per second. This is probably fast enough to give fresh targets for each laser shot, considering most laser repetition rates and spot sizes. But it's something to consider. Okay. Here's an example of an experimental setup where we generate size-selected aerosols that we coat with a nanometer precision shell. So we generate our aerosols here, the sodium benzoate and water, dry off the water. We have sodium benzoate cores where we can size select between the dry sodium benzoate cores are 70 to 150 nanometers. Then the dry cores are heated and mixed with some low vapor pressure coating substance and are cooled together. The dry cores work as heterogeneous nuclei for condensation, and we can grow layers onto them. We can determine the layer thickness by measuring it with another scanning mobility particle sizer and let in some of the aerosol via an aerodynamic lens stack into an experiment. We did velocity map imaging, but you may do whatever you like. Uh-oh. Good. Let's move on to liquid jets. So, many chemical, most biological reactions take place in solutions, often aqueous solutions. Microjets can bring volatile targets of liquid solutions into vacuum, where high-frequency light and electrons are free to roam, and where many measurement techniques can be applied. There are several variations of liquid microjets that have been and are being used. I'll summarize a few of them here. In general, liquid jets, they can be made sub-micron to tens of microns. They're basically, the draw is bulk target volatile sample in vacuum. They have reasonably high signal levels compared to aerosol particles, for example. But they also have their shortcomings, like everything. Good. One way of producing a liquid jet in vacuum conditions is by pushing liquid through either a disc-shaped metal orifice or more often a fused silica capillary. Faubel, Schlemmer, and Tönnes were the first to demonstrate this technique in vacuum in the late 80s. And it was used to collect photoelectron spectra of liquid water, alcohols, alkanes in the late 90s. Over the last couple decades, liquid microjets have been developing quickly and opening doors to several studies that were not previously possible. Like photoelectron spectra of something as volatile as liquid ammonia or liquid ammonia metal solutions, alkali metal solutions. Very cool. The demonstration of a liquid water flat jet operational under vacuum conditions with thicknesses in the micron range also opened up new frontiers in steady state and time resolved XUV and soft X-ray spectroscopies of solution phase systems. This flat jet is produced by crossing two cylindrical jets, as you see here, or one cylindrical jet, two cylindrical jet, to make a flat jet of near uniform thickness that is larger than most laser beam spot sizes. The early flat jets in vacuum produced thicknesses. This one was, I think, between 1 and 3 microns. A later example shows a tunable jet between 2 and 10. So the thicknesses are often on the 1 to 10 nanometer range. They can operate below 10 to the minus 3 millibar. Velocities 10 meters per second. Advantage, I said. This is still, it can be too thick for some transmission experiments, depending on what you want to look at. Luckily, ultra-thin liquid jets down to less than 20 nanometer thickness have been produced using microfluidic gas dynamic nozzles, shown here. Here is a microfluidic chip with a 20 micron central channel where liquid water was pushed through, and two 50 micron channels where helium gas was applied to pinch the liquid jet and flatten it. Here we see increasing amount of helium from 0 SCCM to 100 SCCM, and we see from a cylindrical jet, which would just be the output of the central channel, and increasingly flatter and thinner and wider flat jets. Again, this can operate less than 10 to the minus 3 millibar, near uniform thickness, and is thin enough in most all cases for transmission measurements, if you like that. One of the drawbacks is it does have a higher pumping requirement. The last source I would like to mention is the gas dynamic virtual nozzle. Like we just saw for the ultra-thin flat jet, it uses gas to form a virtual nozzle and can produce cylindrical liquid jets with smaller diameters and less charging than the ones I showed using metal orifices or fused silica. You see the working principle here. Liquid through a capillary, gas pinches the jet as it leaves the valve. And here's a picture of it. You know? These are basically immune to clogging, and they can produce liquid jets with less charging and can produce monodispersed droplet trains, as shown here. I find this really attractive. So this jet can be broken into a stream of nearly identical droplets, solution or pure liquids. By applying a modulation frequency, this can be attractive for producing a stream up to at least hundreds of kilohertz in repetition rates. That said, I'm not sure what the allowable working distance would be for such a particle stream due to turbulence from the significant gas flow around the nozzle. It has, in any case, found some applications already where they use the particle stream directly and where the droplet train is coupled to an aerodynamic lens stack. And I'm sure these will be used more in the future. Achievable droplet sizes so far, from what I see, are around 100 nanometer to tens of microns in diameter. So quite interesting. So we have seen a few ways to generate molecular targets, from supersonic expansions to aerosols to liquid jets. They all have advantages and disadvantages. Hopefully something in that gave you an idea for your future work. Thank you.